this part of the chapter, we will be discussing about the relationship between the stress and the strain. There is a stress and the strain curve that we will be understanding about. So effectively, the stress and the strain curve comes from the different bulk modulus that we have. We have a Young's modulus, we have a bulk modulus, and we have a pressure modulus as well. So combining all of that, we talk about in the case how exactly the stress and the strain curves are related, or the stress and strain values are related. We will understand that the stress and strain values have different levels. There is something known as an elastic limit, something known as a plastic limit, and there is a fatigue limit. So let's try to understand about the different consequences of the different points that we plot. So students, we learned about elasticity. Now we also learned about what is a stress, what is a strain. Now we'll go further into the stress strain part 2. We defined something known as a stress. So what was stress? Stress is nothing but the force that is being applied per unit area, right? So that area can be either horizontal, that is either the force can be applied perpendicular to the area or tangential to the area, but it has to be applied on a particular area. So let's differentiate it between the different types of stresses. So first let's start off with the tensile stress. So if we talk about the tensile stress, so here let's say this is our cross-sectional area that we are referring to. Let me change the color of the pen. Okay, so this is the cross-sectional area that we are referring to, and we are applying a force here and in the downward direction. So this way, what is going to be the tensile stress? So tensile stress will be defined as sigma, which is going to be equals to Ft, which is the force that has been applied on any particular cross section. So mind you, this is here we are not considering both the forces, because both the forces are not acting at the same area of cross section. They are acting at different areas of cross section. So we have to take the stress at a particular area of cross section. So it becomes Ft divided by A naught. So this you can preferably, you don't need to use pounds and all. So it's better that you write down a Newton per meter square. So this is what is known as a tensile stress. Further, if we have to define about the shear stress. So as I mentioned, the previous case was when we talked about the force being applied perpendicular to the area. Now if we would like to say that the force being applied tangential or at a particular angle. So what will we say? Let's say this is my shear stress. So if the force is being applied horizontally, or that is tangential to the area, that results into what? So let me put it this way. So I have the object like this. So this is my object, yeah, and I apply a force. So let me just do it this way. I apply a force. As a result, what happens? This gets extended, so you are sliding it effectively. So if it gets extended, so there is this. So here in this case, if I say theta is here, the original height is here, and the extension produced is here. So in this case, we define how much is the extension that has been produced at a particular height, right? Because if you assume that it's a cuboid, it's a cube, so obviously all the sides are equal. In that case, we can define in terms of the height or how much is exactly the length, right? So if we have to anyways define about the shear stress, so shear stress is defined as the tangential force that you see here divided by the same area of cross section remains the same on which area you are applying the force, but mind you, again the force at a particular area of cross section, not all. In general, if you have to talk about, so if I say I have a force that is acting at an angle theta, so in that case we need to find out the two components, that is there is going to be a horizontal component and there is going to be a vertical component. Both the components have to be taken separately. So the vertical component is going to result into the tangential into a torsion stress, and the horizontal one results into a shear stress. So this is what we get. Now we understand about the strain. So obviously whenever there is a force acting per unit area, that results into a stress. Stress results into some kind of modification in the object. So if I am talking about the tensile stress, so tensile stress does what? Either you apply the force to pull it out, or you push it out. So in both the cases, there is going to be some change in the dimensions taking place. So what are the change in the dimensions? So how do we identify that? So let's say you're applying the force here, so Ft is applied here and Ft is applied here. So as a result, initially the length was L0. Because of the application of the force, we are not changing the volume, mind you. The volume remains constant. So if you are applying the force, obviously what is going to happen, the thickness is going to decrease, right? So if the thickness decreases, the length increases as a matter of fraction. So let's say delta is the increase here, and similarly delta is by 2 is also going to be the increase here. So in all, there is going to be a change in length by delta. So what is tensile strain? Tensile strain is basically the change in length because of the application of force divided by the original length L0. Now if you have to define about the lateral strain, so because of the application of the force, the horizontal width also has decreased. So let's say if I say that initially delta L by 2 was here, similarly delta L by 2 is here, right? So this results, because this gets decreased, the width gets decreased. As a result, we'll say that EL is equals to minus delta L divided by W naught. So this is what is known as the lateral strain. Okay. Now, if we go further, we can talk about what is known as the shear strain. If you remember, we just talked about that if you are applying the force tangential to the surface. So if you are applying the force tangential to the surface, that results into what is known as the shear strain, right? So what is the shear strain? So shear strain basically tells us that how much is the shearing that is taking place. That is how much is the length that is getting extended. I just talked about, I'll just try to refresh it again. As what I said that I have an original object somewhat like this, and then what I do, I apply a tangential force. So if I apply a tangential force, I get the object dimensions changed. So this is what we get. So as a result, theta is the angle that is produced. Okay, so theta is the angle produced. Here if I say that this is y and this is, let's say, delta x, so what happens, we can find out the tan theta value. So tan theta becomes equals to delta x divided by y. So from here we can say how much is delta x by y. So this is the change. So this change is what is represented as gamma. So gamma is nothing but the shear strain that we have. Fine, hopefully this is clear. So what exactly do you understand by the strain? Strain is basically when you apply the force, that is when the stress caused, or for instance your exams give you some stress, yeah, as a result you see the strain lines coming on your face. So stress is being applied because of some reason, and strain is the result that is produced. So that is what we define. So strain is nothing but the relative change in the dimensions of a body because of the actions of an external force. So when you apply or when you give it some force, that results into some kind of a effect. So that effect is the change in the dimension, whether it can be horizontal, vertical, any other dimension. So strain is what? The change in dimension divided by the original dimension. So as you see, it's change in dimension that will have some units, initial dimension that will also have the same units. As a result, strain does not have any unit. So it does not really have any particular unit in it. Okay. Continuing further, like I had stated in the introduction as well, if we talk about Hooke's law. So what is Hooke's law? Hooke's law basically deals with the relation between the stress that has been applied. It was initially done for the case of spring. That's the reason I gave an introduction in the form of spring. But if you talk about in general, Hooke's law basically states that for small deformation, so for very, very small deformations, we say that stress is proportional to strain. That is, when you apply a very small amount of force, such that as soon as you remove the force, the spring comes to its original position. If you apply a huge force, then the spring will not come to its original positions, right? So in the case of Hooke's law, for small deformation, the stress and the strain are proportional to each other. So if I just say that the stress is proportional to strain, so this is, if I say K is the proportionality constant, I should have written plus capital A. So capital K is the proportionality constant. So K is going to be defined as stress divided by strain. Now there will be different types of stresses. So if I just say force per unit area divided by, if I talk about tensile stress, so delta L divided by L. So this particular case, K will be defined as something known as the Young's modulus, which will just come to it. So there are different moduli of elasticity. So K is in general defined as the proportionality constant when the stress is proportional to strain, that is when you do not apply a significantly high amount of force. Okay, let's try to do some examples out of it. So we have a light wire of length 4 meters suspended to the ceiling by one of its ends. So let's say if I just draw it like this. So let's assume that this is my light wire suspended. If its cross section area, so let's say area is 19.6 millimeters square. What is the extension under a load of 10 kg? Okay, so if I say that there is a load that is acting, which is 10 kg, so 10 g, if I say, that's going to be the weight that is acting. Now if I talk about the Young's modulus, so Young's modulus is going to be how much? The force per unit area, force is going to be 10 g divided by area is going to be 19.6 into it's going to be 10 raised to the power minus 6. I have to take it in meter square. 10 g, 10 into 9.8 it is, mind you, divided by the change in length, delta L. Original length is 4, and this is equals to 2 into 10 raised to the power 11. So let's try to simplify this. So 2 into 10 raised to the power 11 into delta L divided by 4, that's going to be equals to 10 into 9.8 divided by 19.6, and this goes as 10 raised to the power 6 here. So from here, what can we further say? Delta L can be given by 2 into, this becomes 98 divided by 19.6 into 10 raised to the power 6 into, this is 10 raised to the power minus 11. So if I just do it, so this gives you 10. Here you get 10 raised to the power 7, so effectively you get 10 raised to the power minus 4 meters. So 10 raised to the power minus 4 meters is nothing but 0.1 millimeters. So this is how it works. Now going further, as I said, the proportionality constant is only going to be existing as long as the object is elastic. That is, as long as the applied stress is proportional to strain. As soon as the proportionality relation breaks, it is no more elastic, right? So for it to be elastic, the stress has to be proportional to the strain. So based on that, let's try to understand about what is the stress strain curve. So if we just try to plot the stress strain curve of a ductile material, ductile is something which can be actually pulled apart, right? Something that is known as brittle breaks down. Ductile is something that can be pulled or it can be stretched, right? So if I say that at the point A you are in the proportional limit. Proportional limit means what? That is, as long as the elasticity is there. That is, as long as we say that the stress is proportional to strain. So till A, the stress is proportional to strain and the Hooke's law is applicable. That is, stress is proportional to strain and you have a proportionality constant, that is K. From A to B, if I talk about this particular limit, stress is not really proportional to strain. So you keep on increasing the stress. So if you basically increase the stress, the amount of strain produced is more. So body is still in the elastic region, but stress is not really proportional to strain. From B to a point D, body is not perfectly elastic. So what happens, this particular point B is what is known as the elastic limit. Elastic limit means it ceases to be elastic anymore. That is, if you apply the force, after the removal of the force, the body may not come to its original state. That is, it ceases to be elastic anymore, right? So body is not perfectly elastic. So permanent deformation starts coming through. So permanent deformation means it starts getting completely deformed. Beyond the point D, it's the fracture point. That is, you keep on extending it. After the point D, let's say if you take a rubber band. So from up to the point A, let's say you extend it slightly. As soon as you remove the force, it comes back. Then from A to B, you extend it more. It becomes thinner, right? From B to D onwards, you keep on extending, the rubber band keeps on extending, it has no more tendency left to return back, right? It has got extended. After the point D, you further extend it, it breaks up. So it breaks up into different constituents, right? So that is what is meant by the fracture point. So what will we have? After the body has a tendency to break, it breaks apart. The closer the break point is to the fracture point, the more it is brittle. The closer the break point, so break point is going to be somewhere, just fracture means there are cracks that are developed, break point means it separates out. So that is what is known. So after fracture, as soon, if you say that the break point is closer to the fracture point, the body will have a more tendency of breaking down at a much faster pace, right? And that is going to be more brittle. If the break point is farther from the fracture point, that is, it gets fractured but it doesn't break out, so in that case it is going to be less brittle. Okay, fine. Based on this, let's try to do some examples. So which one of the following physical quantity does not have the dimensions of force per unit area? It should have been. Okay, so stress does have the force per unit area, is a general thing. Strain is basically change in dimension divided by original dimensions. Obviously it does not have the same dimensions as force per unit area. Young's modulus, if I define it, so it's basically force per unit area. So if I just say force per unit area divided by the change in length upon original length. Obviously the denominator does not have any dimensions, so Young's modulus will have the same dimensions as pressure or force per unit area. Pressure again will have the same dimensions as force per unit area. So effectively the out of the box thing is strain. Moving to the next thing, engineering stress strain curve and true stress strain curve are equal up to, okay, there is something known as engineering stress strain curve, basically where up to whichever engineering materials that you use, they are tested up to a particular limit. Let's say you have nuts, bolts, everything, you test it up to a particular limit. That limit is what is known as the yield point. After the yield point, you do not trust the object anymore, it can break at any point. So these curves are going to be equal up to the yield point. Both the true stress strain curve and in ideal engineering stress strain curve, they are going to be exactly the same up to the yield point. After the yield point, you do not really know how the object may behave, right? You can only predict how it can behave, but there is a large amount of tendency for it to misbehave, right? So yield point is the most appropriate choice in this particular case. Yeah, so hopefully you understood the basic crux of what we talk about in this particular topic, that is stress strain curves and all. So stay tuned for more. Thank you.
Hopefully you would have enjoyed listening to whatever we have discussed in the module. Now, if you still feel that there are any particular doubts that you have, so please visit our site www.askIITians.com. In this, go to the discussion board. Here, you can find all the topics relevant to your questions. You can post your doubts in these relevant topics. And how exactly you are going to do it? Go to the right hand side corner of your screen. As you can see, you can select the category. The categories are defined here. You can select your category, type down your question. You can use your mathematical symbols as well. Else, if you have the question in the form of an image, you can attach the image, post it. We can assure you that the questions would be moderated and answered between 24 to 48 hours after you post it. So keep posting and happy posting. Thank you.
In this part, we discussed about the different relationships that exist for the engineering materials, that is the different relationship with respect to the different points of the stress strain curve. For a rubber band, the stress strain curve may be looking like a different value. For a steel or a soft steel and a hard steel, the stress strain curve will look completely different. So what exactly are the relationships between them, and where exactly is the elastic limit, plastic limit, fatigue limit and all, and the breaking point of all of these substances, we got to know about it. Now we'll continue further and try to understand more deeply about the different types of bulk modulus, how exactly are they related to the different types of stress and the strain in our next part.